Ibrahim asked a question about like, oh, why have these got negatives in here? Why have these got negatives? Shh. The reason I've put negatives into these parts here is because the roots for this damped motion are always going to be negative. It doesn't mean you then make them become negative, but you'll notice that they all have these negative parts in here, and that's because you've got a negative exponential, or e to the minus something, is going to be this kind of shape. So just have a look at the board. These bits have all got these bits featured with the e to the minus at, e to the minus at and stuff here, because e to the minus at looks like this. So it's talking about the parts of the graph following that negative exponential kind of pattern. The only reason that the negatives are in there is because for damped motion, it just will be a negative number. You don't make it become negative, you just follow what the question does, but it has got negatives because it is all going downwards like this, okay? So we are now going to look at a different kind of question, which is called forced harmonic motion. So forced harmonic motion now gives us a bit more, more information, more things that might be happening. So in addition to the natural forces acting on the particle, which could be the damping force and the restoring force, there may be a further force. There may be, that's repeated itself, there may be a further force acting on the particle. This is known as forced harmonic motion. So this particular one that I've got here is this animation. It looks like harmonic motion because it's bouncing back and forth, but the amplitudes of the peaks are getting higher and higher. Okay, if the peaks are getting higher and higher, then it looks like something is being forced to make it move. And the way that this forced motion actually happens is that we go from the type of differential equation that we had previously to one that equals f of t. Who remembers what it is called if it's equal to f of t, not equal to 0?
What, the particular integral?
No, the name of the whole thing. It was begins with H.
Harmonic.
No, that is a word that begins with H, but it's not the one I'm looking for. We say like if it equals 0, it's homogeneous. If it non-homogeneous. Okay, homogeneous means. Yeah, but homogeneous does.
The opposite of homogeneous is heterogeneous.
No, it's non-homogeneous for this, okay? So the only thing that's different now is we have it equaling a function. If it equals a function, what are we going to need to do?
Particular integral.
You're right there, Luke. Yes, it's particular integrals. So it's the same old stuff as before, but we now just have to do particular integrals. So you know when I was saying to you like, yeah, we're going to get tons of practice. So it's just modelling, but of the same thing. So this is what forced harmonic motion looks like. If it's equal to something else, it's going to be just something a bit different. So we're now going to dive in with a few of these examples. A particle P of mass 1.5 kilograms is moving on the x-axis. At time t, the displacement of P from the origin O is x meters and the speed of P is v. I'm just going to pause then for a second and say, okay, here's the origin, here's the particle P, which we know has a mass of 1.5. It's moving, this is the positive x direction that it has over here, and at this stage here it has a velocity of v. So I'm just going to pause at that bit that I've got to. 3 forces act on P, namely a restoring force of magnitude 7.5x. Restoring means going back to the origin. So there's a force here of 7.5x. There is a resistance to the motion of P of magnitude 6v. And there is a force of magnitude 12 sine t acting in the direction OP. This is the direction OP, so there is a force acting to the right of 12 sine t. And we get some information, and then we're going to try and show that this thing is true. So let's just try and name what these forces are. What do you think the 6v, what is that force, potentially? Resistive, so it might be something like air resistance, because it seems to be proportional to the speed. What do you think the 7.5x could possibly be? A spring. It could possibly be a spring that is trying to pull it back to where it was. So potentially we've got a spring with some air resistance, and then there's some other force that is pulling on it, or that is applying this force proportional to, well, not proportional to, at 12 sine t. So it's just going to be something that is doing a different kind of motion that is happening here. So I need to first of all show that this thing is true. How did we show it was true a few examples ago? F equals ma. And I'm going to resolve to the right, and I'm going to use F equals ma. So that's 12 sine t minus 7.5x minus 6v equals 1.5a. So that's 12 sine t minus 7.5x minus 6 dx dt. In fact, I'm just going to use, oh no, I will use dx dt. I was going to use x dot equals 1.5 second derivative of x with respect to time. Rearrange so that this is on the positive side and do what to them all?
Multiply it by.
Divide it by 1.5 because I've got a 1.5 in front of this and the other ones don't. So I get 0 equals the second derivative of x plus 4 dx dt plus 5x. Oh, I don't know why I've got 0 because I'm going to leave the 12 sine t on that side. And when I divide that by 1.5, I get 8 sine t as required. Okay? Now we're going to do part B, which is to find x as a function of t. This is basically what the whole question is about. 2 marks, loads of marks, 1 mark. So let's do the loads of marks part. So let's go kind of speedy here. First of all, we'll do the auxiliary equation. And the auxiliary equation is m squared plus 4m plus 5 is 0. No.
M plus 1, M plus 1, M plus 5.
No.
Minus 2 plus or minus I.
So m is equal to minus 2 plus or minus I. So the complementary function, because remember it's a complementary function now and not the general solution, is x equals,
e to the minus 2t.
good,
P cos
T.
t plus p sin t.
Oh, they both have a sign, so we have to add another x to it. There's another sign here, isn't it?
no, because this is actually an e to the 2t mixed with a sign.
So it doesn't count?
No.
Okay.
At least I don't think it will. We'll find out if it all goes
It
wrong.
will be grouped, when you put all at the end, if it will be grouped together, that's when you do it.
So now we're going to do the particular integral, and we are going to try what? Bearing in mind it's an 8 sine t here.
So it's lambda sine.
So we're going to try x equals lambda sine t
Plus mu cos t.
plus mu cos t. Have to have both of them in there. And so differentiating that with respect to time, we get lambda cos t minus mu sine t. And then the second derivative, minus lambda sine t minus mu cos t. And we're going to substitute that into that. Okay? So we've got the second derivative one, which is minus lambda sine t minus mu cos t. Then we've got 4 lots of this one, which is plus 4 lambda cos t minus 4 mu sine t. 5 lots of the top one, which is 5 lambda sine t plus 5 mu cos t. I didn't quite give myself enough space, and that's all equal to 8 sine t. Good. So we compare the coefficients. First of all, we'll compare sine t. Sine t, we've got minus lambda minus 4 mu plus 5 lambda equals 8. So that's 4 lambda minus 4 mu equals 8, or lambda minus mu equals 2. If we then compare cos t's, we've got minus mu plus 4 lambda plus 5 mu equals
0.
So you get 4 lambda plus 4 mu equals 0. So lambda plus mu equals 0. What shall I do with these equations? This one here and this one. I think I can't even bother to get the calculator out, so I'll just add them together. So I get 2 lambda is 2, so lambda is 1, which means mu is minus 1.
And then we put that in and then add them to the complementary.
So the particular integral is x equals lambda sine t, which is just sine t, plus mu, which is minus cos t.
And then we add it to the complementary.
Yep.
So the general solution.
The general solution is x equals the complementary function plus the particular integral. So that is e to the minus 2t sine t plus cos t.
P sine t plus q cos t.
Oh, thank you, yeah.
Yeah, I was going to say, if you had
Did we do it sine then cos? We did, didn't we? We did P sine T. Or did we did cos first, didn't we? It is always cos that we do first. Yeah. Let's not mix it up halfway through. P cos T plus Q sine T plus this thing, sine T minus cos T.
And then we use the information given.
And then the information given was T equals 0, x equals 5, dx dt is 2. T equals 0, x equals 5, dx dt is 2.
Oh, now continue what we did before.
So let's sub in t equals 0 and x is 5. So we get 5 equals, subbing in 0 here, p, subbing in 0 here,
1.
minus 1. So p equals 6. Now I'm going to differentiate it. So dx dt equals
Oh, look. So it's
minus 2 e to the minus 2t,
and then what is that?
p cos t plus q sine t,
Then it's
plus e to the minus 2t,
minus p cos sin t, and then plus q sin cos t. Ah!
and then sine goes to cos, and minus cos goes to sine.
Why are you not dying? Relax.
This is just differentiation. And we know that dx dt is 2. So 2 equals minus 2 multiplied by p plus q plus 1.
What did you not do?
And p is 6. So you get 2 equals minus 12 plus q plus 1. So that's q is 13. So x equals e to the minus 2t, 6 cos t, plus 13 sine t, plus sine t minus cos t. What is going on here?
Who's laughing?
Okay, let's have a look at what this looks like. Please get a grip, guys. So y equals e to the minus 2x in this case. 6 cos...
Why are you laughing now? What's happened? I'm missing something.
Okay, so this is how it behaves. So it starts off doing this, and then what does it look like it's doing over time?
Lightly down.
What happens after t becomes big? What
Keep going.
about if I showed you this? It looks like simple harmonic motion. Sorry, I didn't hear that in our head. Just going to be simple harmonic motion. Why is it simple harmonic motion after a long time?
Because there's an extra force added.
Look at this and see if you can tell me why it becomes simple harmonic motion after a long time. Yes, you're right about the extra force that's been added, but why is this, over a long period of time, going to turn into it? Pardon? What? Tell me more.
Oh, the negative e tends to 0.
Yeah, this is
Then
going.
we've just got a sin t cos t.
So when t becomes big, this disappears,
Yeah, that makes sense.
which means you're left with just sine t minus cos t. And we know that sine t minus cos t is a harmonic identity, which is just a combo and is just another sinusoidal curve with period 2 pi. So if we go back to this, you should notice that the gap between them is like what, roughly 10 and like 16. Yeah, that's about 2 pi, isn't it? 6 seconds, 2 pi.
Sorry.
So let's just finish up what it says. Find x as a function of t. Describe the motion when t is large. So part C, when t goes to infinity, e to the minus 2t goes to 0. So x goes to sine t minus cos t, i.e. As t becomes large, motion is simple harmonic motion.
Because I means in other words.
Basically, yeah.
Okay.
but it comes from Latin, I think. IE stands for something in Latin.
I always just thought it's an example.
No.
That doesn't make sense though, does it? Now I think about it. An example.
Even when you think EG, there's
What's
no.
EG?
It also, I think, comes from Latin because there's no G in example.
I know, but
It's not.
Yeah, but it's like the eggs there, isn't it?
there's some video as well.
Example.
Yeah, some genius example.
Okay, because of all the giggling and laughter, after we do the next example, no one is leaving until we've done this exam question and another exam question.
Together.
Even
Yeah,
me.
you got. I'm not going to be doing it. You've got to do it yourself.
Oh, by ourselves, right? That's
Yeah.
fine.
Okay, I'm going to do one more now, and then we're finishing up.
It's not fair.
Wait, what? I thought you said we did.
No, you're going to be doing this one before you leave.
Oh, calm. Minor.
Okay, so a particle P is attached to the end of a light elastic string. Blah, 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 blah. Initially, the particle and the string lie at rest on a smooth horizontal plane. Time t equals 0, the end B of the string is set in motion, which moves with constant speed u in the direction AB, and the displacement of P from A is x. Air resistance acting on P is proportional to its speed. The subsequent motion can be modelled by this differential equation. So really all it wants us to do is to solve this differential equation, okay? I'm not actually bothered about any of the modelling that's going on here because it hasn't asked me to show that that is the model. It just wants me to find an expression for x in terms of u, k and t. Okay, let's go.
It's minus k.
So auxiliary equation,
N squared plus 2km plus k squared equals.
do we remember what the solution of this was?
Minus
Plus
k.
or minus.
It's a repeated.
Minus k plus or minus
Ki.
ki.
No, but there was a 2 in front of it.
No, it's
No,
not.
this
No,
one
it's
is
just minus k repeated.
Minus k.
Yeah,
Oh yeah,
it's just minus k repeated.
sorry. It's minus m,
Equals minus k.
it's m plus k squared.
Yeah.
So m is equal to minus k. What type, if this was just heavy, what type of damping would it be? It would be critical. It would be critical, but we know it's forced.
I just realised I said damp. It's just
But we know it's not going to be that because we've got some other forces that are going on here. So our complementary function is x equals a plus bt e to the minus kt. Okay? Particular integral, what are we going to try for x if it's equal to 2ku? Pardon? Just lambda. Because this is a constant, this is a constant, this is a constant. So obviously x dot is 0 and x double dot is 0. So when we sub into this, we just get 0 plus k squared lambda equals 2ku. So lambda equals 2u over k. So that must mean that our general solution is x equals a plus bt e to the minus kt plus 2u over k. I don't know. Do we think we can find any of these things? I think there's some things that we can find here. I think
we
there's.
need to be able to find A and B.
I think we need to find A and B. What does it tell us?
Standard U, K and T.
So what else does it tell us? When t equals 0,
The end of the string is set in motion.
V
and
equals
moves
U.
with constant speed v. So V is U.
is it? It says initially the particle and the string lie at rest on a smooth horizontal plane. And t0 is the end of the string is set in motion and moves with constant speed u. Yeah. So I think v is u.
So
Why does it
first
stay-
line it says
But it says it's at rest.
it says at the first initially it's at rest. Then it moves
the
on.
end of the first line.
So V is 0. Everything's 0. The one is 0.
For real.
Oh my god.
Omega L. You're an omega L. Yeah, fat.
No, the speed is u.
What about the first one?
Because I think it's like, you know, when it has a question, it says it's not doing anything, and now we've projected it at this speed at the start. So I actually think that v is equal to u. So in other words, dx dt is equal to u. What do we think x is at the beginning?
0.
It's just
What's x? The
Guys, can you
displacement
like just
of P from A is x on the third line. after the U part.
I think it's implying that it's... I think it's implying that at the beginning it's at... Why is everyone just constantly talking? I'm trying to think here. The end of B is set in motion and moves with constant speed in the direction AB. So I actually just think A and B are starting at the beginning and then it's being set off. So actually what's happening here is A and here is B and they're connected with a long piece of string, and B is being moved in this direction with a speed of U, and we know eventually it's going to then start bouncing after a while, okay? So I actually think it's implying, and it's not particularly clear, I agree with you, it's not particularly clear. I think when it's starting, it is saying that it hasn't displaced at all. I don't know how clear that is, but it's just saying that...
So it's at the point where it hits it, that
Yeah.
you hit B to move it.
Yeah, I think so.
Okay.
It's not particularly clear. I don't necessarily agree with this thing, but this is the way that the example is actually done.
You could kind of guess it because it says in terms of U, K and T.
Yeah, so we've got to know that it's 0. There's nothing else they've told us. If they haven't told you where else it is, it's probably got to be 0. So we'll just do the same old of subbing in these things into our general solution. So we get 0 equals A plus 2U over K. So A is minus 2U over K. And then we'll differentiate it. So dx dt is minus K A plus BT e to the minus KT. When you differentiate this, it just goes. Oh, I haven't finished differentiating this either, have I? Plus B e to the minus KT. And we know that the dx dt is U when t is 0. So you just get minus K A plus B. But we know that A is that. So U equals minus K multiplied by minus 2U over K plus B. The minuses and the K's cancel, so U equals 2U plus B. So B is equal to minus U, which means that X equals minus 2U over K minus UT e to the minus KT plus 2U over K.
Is that what the book says?
X equals minus 2U over K minus UT e to the minus KT plus 2U over K. Yep. So we can now do the rest of exercise 8C. Same old, there's nothing really new here, which is why I kind of rushed us through some of the other bit. But what I think might be quite interesting for us to try before we leave is this car question here. And if you're looking back on this and you're looking at the video, what I'm probably going to do is leave that question and I'll put the mark scheme here and then I'll finish recording there so that if you want to know if you've done it right, you can pause the video and have a look at this, okay?